The relationship between pKa and pH, extraction using a separatory funnel. Have you got it? This video quiz assesses your understanding of how pKa and pH are related, your ability to determine what the principal species in solution will be when compounds or mixtures of compounds, particularly acids and bases, are dissolved in water and adjusted to a specific pH, and how you can use that knowledge to design laboratory procedures to extract a desired product from other compounds after running an organic reaction by extraction with a separatory funnel. This quiz consists of 3 questions. It's meant to be taken after you have studied the material and think you understand it. During the presentation, you'll be asked to pause the video, at least try to solve the problem yourself, and only then continue. It won't be hardly as effective if you jump to the solution immediately. Okay, here we go. Number 1, benzoic acid is added to water. The pH is adjusted using 10% aqueous HCl solution or 10% aqueous sodium carbonate. For each of the pH values given below, draw the structure of the species, the compound or its conjugate base that will predominate at the specified pH. So pause the video for a moment while you think about this. It really shouldn't take you long. If you want to write it in there, you can. Otherwise, just think about it, and we'll continue when you're ready. All right, here we go. Okay, we see that the benzoic acid has a pKa of 4.2. So that means at a pH of 4.2, we have a 50-50 mixture, a 1-to-1 mixture of benzoic acid and its anion. And at pH 2.2, then, by adding HCl, driving that pH to a more acidic value, what we've done is we've pushed the equilibrium even further toward the benzoic acid. So at this pH, it will be almost exclusively benzoic acid. By adding sodium carbonate, which is a base, we can drive this pH to higher number. In this case, 11.7, hugely more than 4.2. There's hardly a trace of that acid in, and instead, now what we've got is the anion. Okay, nothing more than that. It's just compare the pH to the pKa. If the pH is much lower than the pKa, then you need to get that proton on the structure. If the pH is higher than the pKa, then you want to have the deprotonated form. Number 2, the 3 compounds below with the indicated pKa values were added to 50 milliliters of water, creating a solution that was tested and found to have a pH of 5.2. The pH was adjusted to 8.0 by adding 10% aqueous sodium carbonate. For each of the compounds, draw the structures of the 2 species that you would expect to find in solution, an acid form and a base form, and indicate which of the 2 will predominate at this pH. Okay, so pause the video, make a little table, and fill in the information. You have benzoic acid, pKa of 4.2, aniline with a pKa of its conjugate acid of 5.0, and phenol with a pKa of 10.0. Target pH is 8.0. What have you got in that solution? Okay, here we go. For benzoic acid, we have protonated form and deprotonated form. For aniline, conjugate acid of aniline has an extra proton, and its deprotonated form this time is neutral. And phenol is like benzoic acid. Protonated OH, deprotonated anion. Okay, so now what we know is that this solution is at pH that's much higher than the 4.2, much more basic, the equilibrium is driven to the anionic form. In the case of aniline, pKa also in this range around 5. Again, pH of 8 is above this number. It's going to be driven to its neutral form, the aniline itself. And phenol with a pKa of 10, since now 8 is lower pH than that pKa value, it's more acidic than the point where it would be 50-50. That equilibrium is also driven to its neutral form. So at pH 8, we have one anion and 2 neutral forms. Okay? Number 3. Okay, this is a pretty good challenge. Describe what you would do to separate the 3 compounds from the solution described in problem 2. You have at your disposal 2 separatory funnels, several Erlenmeyer flasks, and 100 milliliters of ethyl ether, as well as 10% aqueous HCl and 10% aqueous sodium carbonate, and a pH 7 phosphate buffer. All right, see what you can do. Think about how you would change that pH to different values to try to pull out an anionic or a cationic species into the water, leaving the others in the ether, or however you want to think about doing it. Okay? Okay? So pause the video. When you're ready, come back when you think you've got something, and we'll talk about it. Okay, we're back. Well, how are we going to do this? Let's think about it. We just saw on the previous slide that at pH 8, for example, we have an anion from the benzoic acid, and we have neutral for the aniline and neutral for the phenol. That says that if we bring this to pH 8, what we can do is pull out the benzoic acid as its anion from the other 2 compounds. Okay, this is a water solution. So in this first pass, if we were to do this at pH 8, the phenol and the aniline would be extracted into ether, separating out the benzoic acid in water. Okay, now if we did a second pass, what we could do is we could add a solution which would pull one of these 2 compounds into it. And with a pKa of 5 of aniline, what do we know? Well, if we go to a pH of 2, then that will protonate this species and we'll get the plus charged aniline. Another alternative would be that if we were to go to an even higher pH, like 11, then we could pull this hydrogen off the phenol and we could make its anionic form. So we actually have some options here. We can either go acidic and make the NH2 positive as a NH3 plus, or we can go to much more basic solution and take out the phenol first. It's really up to you. What I'm going to do is go acidic. So I'm going to add HCl, and we're going to take that to pH 2. Now what's going to happen is that in the water, what we're going to have is protonated aniline, and in the ether, we have our phenol still. Okay, so in this process, what we have done is separated out the 3 compounds. They're now all in separate flasks. Remember, the pKa of an acid or conjugate acid of a base is the pH where half the compound is in its protonated form and half is in its deprotonated form. Depending upon the pH of a solution containing the acid or base, the predominant form will be either the protonated form at pH less than pKa or the protonated form at pH greater than pKa. We can have full control of the pH of a solution by carefully adding acid or base or by using a buffer at a specific pH, such as pH 7 phosphate buffer. By adding ethyl ether, which floats on the top of the water and extracts into it only neutral compounds, not ions, we can extract compounds from an aqueous solution using a piece of glassware called a separatory funnel. Remember, a convenient way of describing an extraction procedure is with a flowchart that describes the steps taken. Careful control of pH allows separating multiple compounds using multiple extractions. And I note here that in most procedures that are actually done in the lab, the extraction is done 2 or 3 times to make sure that all of the compound, or virtually all of the compound, is separated and extracted into the desired layer. Okay, well, I hope that was helpful, and I hope you got it.